Hey everybody, this is video 3 on measurement and precision. We're going to be talking about significant digits. So here we go. There's really two types of measurements. There's exact and inexact, and really an exact measurement, it's not much of a measurement at all. For example, I see there are 5 apples here. I didn't have to have any sort of measuring device to figure that out. There's no uncertainty. 1, 2, 3, 4, 5, there's 5 apples. An inexact measurement, though, is a different story. When we make an inexact measurement, there's some estimating involved. For example, if you're looking at this thermometer right here, it appears that it's 87, between 87 and 88. So we would call that 87.5 degrees. I think this is Celsius. But I'm not really positive about that. Like, you could convince me it's 87.4. So that's what I mean by we have to estimate it. So there are two things that affect an inexact measurement. One is how precise the measuring device is. The second is the skill of the person making the measurement. Do they know what they're doing? Do they know how to read the instrument? Now, when we use a digital device, whether it be a digital balance, like these, or digital thermometer, this is a digital pH meter. These things are rounding off too. When you step on a digital bathroom scale, do you think you weigh, for example, exactly 143 pounds? The device is rounding it off. That last digit is rounded. This balance only rounds to the 10th of a gram, it appears. This one rounds to the 100th. Wow, this one rounds to the 10,000th of a gram, okay? But all these measuring devices are rounding off themselves, so they're inexact measurements too. But when we don't use a digital device to make a measurement, we have to estimate it, and this is where our skill comes in. So if we're reading this nail, this blow up right here of the length of that nail in centimeters, we can see that the point lies, looks like it's dead center between 6.3 and 6.4, and so we're going to estimate that to 6.35. Since this ruler here is graduated every 10th of a centimeter, we're going to estimate to the 100th. Okay, take a second and pause the video and look at these 3 pictures and see if you can estimate the measurements there. Okay, so in this one here, looks like it's this whatever this liquid is, water probably, and this graduated cylinder is at between 52 and 53. The line there, by the way, we call that line the meniscus. Seems to be right at 52.0, 52.9 maybe, I would call that. Notice that I'm having to estimate the 9. I mean, you could make an argument it's 52.8. Over here at this thermometer, that appears to be about 17.0, I don't know, 3 maybe. It's hard to say. I'm not really sure about the 3. I know it's at least 17. Down here, these 2 nails, the first ruler has a lot more graduations than ruler B. So in ruler A, I would say that nail looks to be about 4.3, and not quite 4.4, I don't think. I think it's 4.39 centimeters. This one, well, there's not as many graduations. The best I can do is estimate that one to the 10th place, so like 4.3. So notice that these measurements reflect the precision of the measuring device. So the number of significant digits in a measurement includes the digits we're sure of, plus the first uncertain digit, plus the first one we have to estimate. So looking at this ruler here, trying to read this green line, it looks like it's between 2.7 and 2.8, so I'm going to call it 2.7, 38 centimeters. So that number has 3 significant digits. We had to estimate the first uncertain digit. Look at the graduated cylinder over here. Reading that appears to be 63.04 maybe. So 63.4 milliliters. I had to estimate that one, that number, that measurement has 3 significant digits. Now, on a digital balance, it's easy. They would do the rounding for you. So this mass right here would have 6 significant digits. Here's another digital thermometer here, and this appears to be between 38.4 and 38.5. So 38.4, 38.4, about halfway, 38.45 degrees Celsius. Therefore, we had to estimate that one. That's 4 significant digits. Okay, what if a measurement appears to be right on a number, appears to be exact? Like these are 2 centimeter rulers, but this top one here it's not graduated every tenth like the one down here is. So if I'm measuring this green line here right on 2, because there's no 10th graduations, the best we can do is say that's 2.0. To help you understand that, what if the line had been right here? Well, you would have estimated something like 2.5. And so we have to reflect the precision of this ruler when we report that digit, even if it's exact. So down here then, using that same logic on this bottom ruler, since this thing is divided every tenth, we estimate to the 100th. Okay? So if that line is right on 2, we need to report this measurement as 2.00 to show that this ruler, this measurement, was made on something pretty precise. Okay? To help you understand that, what if the line had been right in here, right in between 2.3 and 2.4? We would have called that something like 2.35, okay, to the 100th place. And so even if it's exactly right on it, or it appears to be, we still have to show those zeros there. So I guess what we're saying here is that the number of significant digits that you show in a measurement says something about the precision of the device that was used to make the measurement. So here's an easy one. Which of these 3 balances do you think was used to measure something that had a mass of 3.48 grams? Well, obviously it couldn't have been this one. That only goes to the 10th of a gram. Here, we got 3 decimal places. Had to be this one. So we're going to be measuring a lot of things in class, but we're also going to be working a lot of problems where other people have done the measuring, and we just assume that they're following the same rules that we are. So if we see a measurement like that, that has 4 significant digits. If we see something like that, it has 3 significant digits. Now, what if the mass is in scientific notation? Like this is 5.12 times 10 to the 21st, let's say grams. Well, the nice thing about these is you don't have to worry about the 10 to the 21st. You're just looking at the first part of the measurement, the 5.12, and therefore that measurement has 3 significant digits. So here are the rules for significant digits. Sorry, the slide got messed up here on number 1. Non-zero digits always count. So 892.42 grams, that one has 5 significant digits. 3.5 kilometers, that has 2. So if it's not a 0, it always counts. Of course, that makes you wonder, what's the deal with zeros? Well, there's one situation where zeros are always significant, and there's another situation where they're never significant. Zeros are always significant when they're sandwiched between 2 non-zero digits. Okay, so like this one, that's a captured or sandwiched zeros. Both of those are. So that has 4 significant digits. This 0 is stuck between the 5 and the 4. That has 3 sig digs. And so captured zeros are always significant. Zeros at the beginning of a number, however, they are never significant. Okay? So down here in this 0.539 milligrams, that leading zero is not significant. It only serves as a placeholder. To kind of illustrate that, if we wrote 5.39 times 10 to the negative 1, if we express that number in scientific notation, you can see that the zero kind of disappears. You know, it's accounted for here. That leading zero is just a placeholder. So that number has 3 significant digits. Down here, 0.003642, that could be expressed as 3.642 times 10 to the negative 3. Notice there are only 4 sig digs there. So zeros at the beginning of a number, leading zeros, are never significant. So with zeros, we've got an always situation, we've got a never situation, and here we've got a sometimes situation. Here's the easiest way to remember it. If the number has a decimal in it, then the trailing zeros, the zeros that come at the end, are significant. So 23.0, notice the decimal, that zero, that trailing zero counts. That has 3 sig digs. 23, actually what I should have put is 230. 230, notice there are no zeros there. No decimals there. That only has 2 significant digits. This number, because of that that decimal at the end, it has 5 sig digs. All those trailing zeros count. But this number, with no decimal, would only have 2 significant digits. This value, golly, we've got every situation. These leading zeros don't count. That zero does because it's captured, and the decimal right here makes that trailing zero count. So that has 5 significant digits. So if you're having a problem understanding that trailing zero thing, think about it this way. If we have a measurement report at 12.23 centimeters, we just assume we've got a measuring device where the best we can do is estimate it to 2 decimal places. Okay, so that one would have 4 sig digs. But if that measurement was reported as this, those 4 decimal places tell us that we're using a device that's a lot more precise, and we got to count those zeros. And so that gives us, in this number, 6 decimal places. 6 significant digits. So take a look at these, and you can see that top one there has a decimal, making that trailing zero significant. Take a look at that one. Leading zeros aren't. The trailing zero is because of the decimal. None of these zeros are significant, but all of these are because of the decimal. Okay, try these on for size. Pause the video, try these. Okay, if you said 4, 2, 2, 3, 8, 3, 4, you were right. So back to one of the first slides. What if you got an exact measurement? How many sig digs? Well, since we don't use a measuring device, there's no uncertainty, and there's an infinite number. Here's one to think about. Thanks for watching.